A group of boffins from the Applied Electromagnetics Group at the University of California, San Diego have succeeded in building a microelectronic device without the incorporation of semiconductors for the first time, at least in a published paper. It's certainly possible that the feat has been accomplished in a secret military facility or by a want-to-be Bond villain, but this research was published this week. Fighting Moore's Law by Abandoning Semiconductors. The team published its findings in Nature Communications this week, explaining how they were able to engineer an optically controlled device that bypassed by the use of semiconductors by thinking of and employing a metasurface in the nanoscale that avoids the limits that superconductors bring to electron flow, or, perhaps more familiar, conductivity. Electrons have a pesky habit of running into a number of atoms on their way to a given point in a semiconductor, but the team worked out a vacuum tube 2.0 that avoids the limitations placed on power handling and speed that semiconductors bring. Work with my layman understanding of how this was accomplished with the knowledge that I'm working from my own brain's limitations when quantum or nano understandings are brought to the table, in spite of near prodigy level mathematical understandings I once possessed but are challenged terrifically before being blown away by these innovations. By using a less than 10-volt DC charge and infrared laser on a metasurface the team made to rest on a silicon wafer with a layer of silicon dioxide, they found they could make their chip work. On a nanoscale, the researchers couldn't simply apply high-powered lasers that would have replaced the need for the metasurface used to boost conductivity owing to the heat that lasers would produce. This certainly won't replace all semiconductor devices, but it may be the best approach for certain specialty applications, such as very high frequencies or high-power devices, said electrical engineering professor Dan Saventpiper at UC San Diego's Applied Electromagnetics Group, who led the team and was the lead author of the paper published this week. Next, we need to understand how far these devices can be scaled and the limits of their performance. Moore's law dictates that computing speeds double every 2 years and are meant to see a consequent drop in cost, and the team recognizes that they are onto something impractical beyond their existing accomplishment. We're years, if not multiple decades, away from the replacement of the semiconductors that power more and more of our lives each day. Yet, we still see silicon pushing the boundaries of its capacity. Thinner and faster will still be the way forward as power needs decrease, but ionic traps and the programming of the atom, only covered a touch over a century ago, are the future, and these kids are smart. The work done by this team showed that the use of low-power lasers and DC power clearly illustrate that when applied to the correct surfaces can replace the need for a high-powered laser, but scalability and further advances will have to wait another 5 years. When Elon Musk presented his white paper on the Hyperloop, he was scoffed at, but others have run with this, and it shows the power of outside-the-box thinking with talented individuals doing the thinking. Scientists make semiconductor-free chip that work similarly to vacuum tubes. Scientists have devised a metamaterial that liberates free electrons, sort of like vacuum electronics. The resulting semiconductor-free device operates at speed, wavelength, and power handling far greater than what's available today. On May 10, 1954, in front of an audience of baffled scientists and engineers, Gordon Teal of Texas Instruments Incorporated made one of the most important announcements of the past centuries. Teal carefully pulled out several objects out of his pocket and immediately jaws dropped. These were silicon transistors. Today, probably 95% of all semiconductors, essential materials for any electronics component, are fabricated from silicon, despite the first transistor was a germanium device. Before silicon or germanium transistors came along, however, all electronics used vacuum tubes in their construction. These tubes consumed a great deal of electrical power and gave off enormous heat, so the transistor was seen as a fantastic upgrade, ushering a new age of miniaturization that continues to this day. However, these wonder electronics aren't perfect. Some electronics applications feel the limits of silicon transistors because the velocity of electrons is limited by the resistance of the material. To get these electrons flowing through the band gap between the semiconductor's insulating and conducting properties, you need to supply more juice. Researchers at the University of California, San Diego sought to get around this problem by taking some hints from ancient electronics history and reverting back to the principle of operation of tube electronics, which involves free electrons. World's first semiconductor-free tech can make CPU chips faster than ever. Until now, silicon is the material that powers most of the microelectronic devices. It's omnipresent and its existence is so prominent that the Silicon Valley has been named after the material. All of the fastest microprocessor chips out there feature millions of closely packed silicon-based tiny transistors. But the fact that silicon is a semiconductor material having conductivity between metals and insulators, which puts a limit on a device's conductivity and, eventually, on the processing power. A band gap exists for the semiconductor materials, and in order to enable the flow of electrons across the material, the electrons need an extra push given by applying a voltage to cross the band gap. Still, the electrons move slowly as they constantly bump into the atoms while they travel across the band gap. Researchers at UC San Diego have tried to address this issue by ditching the semiconductor material for free electrons in space. The technology is similar to the century-old vacuum tube-based computers in which the flow of electrons occurs in free space. But it isn't possible for microscale devices as it requires applying a high voltage, more than 100 volts, high-powered lasers, or high temperatures to kick the electrons from the surface of the material. The team led by Dan Savent-Piper worked out a solution for their reincarnated tech. Their microscale device consists of a metasurface featuring an array of gold mushroom nanostructure on parallel gold strips. This metasurface sits on top of a silicon wafer and has silicon dioxide layer in between. By applying a low DC voltage, below 10 V, and using a low-power laser, enough energy can be generated which is sufficient to kick out electrons from the gold metal. The new tech, currently a proof of concept, is able to deliver 1000% change in the conductivity. The paper is published in Nature. The electron-emitting surface is scalable and can handle high power. Such devices can be used as transistors, photodetectors, or power amplifiers. The world's first semiconductor-free and laser-controlled DARPA-funded project can be beneficial for electronic devices, photovoltaics, or environment applications. The technology looks promising, but the researchers aren't aiming it as a full-fledged alternative. This certainly won't replace all semiconductor devices, but it may be the best approach for certain specialty applications, such as very high frequencies or high-power devices, said Savent-Piper. According to the researchers, for different microelectronic devices, different metasurfaces will have to be designed and optimized. To more about the metasurface, you can read the research paper on Nature.